Uh, Good morning, everyone. Can you all hear me clearly? Okay, for confirming that. I want to welcome you to my lecture today. Of course, today we're going to be focusing on another exciting statistical topic. Okay, that we'll call instrumental variable regression. Okay, so focus today will be on instrumental variable regression. Okay, so in the outline, basically, we're going to we're going to revisit the OLS assumptions and, of course, what happened when they are violated. Then I'm actually going to introduce everyone to instrumental variable approach. Okay, under the instrumental variable approach, we could talk about one endogenous regressor, one instrument. Okay, and we could also talk about one endogenous regressor, one instrument and control variables, and one endogenous regressor and multiple instruments. We're also going to discuss multiple endogenous regressors and multiple instruments. And at the same time, we're going to talk about assumptions underlying the use of instrumental variable, okay, the instrument relevance and instrument exogeneity. Okay, so we're going to kickstart with the problem of endogeneity in econometrics. And I want to say what we mean by endogeneity. You know, the endogeneity actually occur when the set of features, the explanatory variables you are actually using correlate with the error time. I want to remind you that one of the assumptions of OLS is that, the independent variable or the predictor variable used should not correlate with unobserved. And the moment when that happens, then it means it's no longer truly exogenous. It becomes endogenous in a way. Okay, so an endogeneity can actually, arise maybe as a result of measurement error or the autoregression with autocorrelated errors or omitting variables. Of course, you're basically going to learn all of that today. So what causes this and how can we actually fix that? So which means the takeaway from this is just like, okay, whenever we specify a functional form of a linear regression model, and of course, assumption is basically on the error time, and the moment one of the independent variable or the one we call explanatory variable or predictor is correlating with the error time. Don't forget the error time here is basically the unobserved. Then in that kind of situation, the endogeneity issue arise. Okay, some of you may be wondering, in my previous class, we talked about relationship among the explanatory variables, situation where they correlate, where the independent variables actually correlate, that lead to multicollinearity, right? Now, what is the difference between multicollinearity and the endogeneity? Okay, of course, difference exists between the two. The endogeneity is talking about the correlation of your, predictor, predictor variable, or the one you call explanatory variable, okay, with the error time. But why multicollinearity only talk about correlation among the explanatory variables in your model? You can see the two of them are not the same. So multicollinearity is not the same as endogeneity. I'm actually going to say that again. When there's a serial correlation among your features, among your explanatory variables that we also call predictors variables. Okay, when there's a relationship between them, we call that multicollinearity. Of course, we are still talking about relationship between they are observed, but when you're talking about relationship between the observed and unobserved, that's what we talk about here as endogeneity. So which means we don't really expect independent variable to be correlating with the error time. You get what I mean, right? And if that happens, then we have the problem of endogeneity. Now, on this slide now, I basically want to explain how do we actually fix the endogeneity concerns. Because if you don't fix that, there's basically going to be an issue because we may not be able to trust, the estimates of the regression parameters anymore. And that is the reason why we need to fix that in order not to mislead scientific community. Okay, so the best way to actually deal with that issue is when we make use of instrumental variable technique. Okay, and that is why we basically call in this instrumental variable regression. Before I actually move on, is there anyone who want to ask question or who need clarification? Okay, so which means you guys are good. Okay, so the best way to fix the problem of endogeneity now is basically to use instrumental variable technique. And when we're using instrumental variable technique, we're basically going to have a new estimator, like the estimator that we have in the conventional linear regression. The conventional linear regression was actually performed on a single stage. But now that the instrumental variable is actually involved, okay, that will be done in 2 stages. Okay, that will be done in 2 stages, and I'm actually going to explain each of the stage. So we basically going to call that estimator 2-stage least squares. Of course, the 2-stage least square because we're actually going to apply our OLS in 2 stages. And we're going to talk about this when we're trying to, or this is necessary when we're trying to fix the problem of endogeneity, okay, via instrumental variable technique. Okay, so if I were to use instrumental variable technique to solve the problem of endogeneity, then I need to be able to investigate the behavior or the authenticity of the instrumental variable. Because right now, the instrumental variable is basically going to be a third variable, okay, that we actually want to use in the regression. Before we use that third variable, okay, when we in a situation where the relationship between the outcome variable and the predictor is actually influenced by other variables in the model. Of course, you're basically gonna see, you've heard about it before. I remember when I was teaching a concept of prediction and explanation in class, when I was talking about a particular tension called causation versus association. And of course, the reason why in statistical analysis, why we cannot conclude causation, when we're dealing with the association because of the third variable problem. Okay. Now, this is actually similar to that because the instrumental variable you actually going to incorporate into your model to fix the problem of endogeneity is actually believed to have a connection, okay, between, the response and the predictor that you are using. Okay, so we want to have an example now from a real life practical situation. Okay, so an an example of instrumental variable. When you take a look at the relationship between wages and education, okay, and you realize that relationship actually depend on another variable, and of course initially that variable was not part of the statistical architecture. That particular variable was actually incorporated in the random part. And of course, when you are trying to bring it out from the random part now, you actually want to use that to fix the problem that in the name of instrumental variable. Okay, so we are looking at the effects of education on wages, or probably return on education. And um, there's a particular third variable which we call the ability. Okay, the ability, maybe it may be the ability to combine maybe work with education. Maybe you are kind of person, maybe we're using the observational unit that that they are in university, and at the same time they are working. And of course, the third variable here may basically be ability to combine both. Okay, ability to combine education with work. You get what I mean? So that is similar to what I'm discussing here. Even though that ability was not directly observable, of course, it may influence the relationship between the two variables of interest. Okay, so we can actually use available test score to proxy, okay, for that ability. Okay, so the purpose of instrumental variable now, of course, they are used to control for confounding a measurement in observational study. You remember the other time, the reason why we cannot conclude causation on association is because you know you do association with observational study situation where you want to come into a conclusion if you're able to establish that there's a relationship between two variables. Of course, that doesn't mean one causes the other. Okay, because the reason why you may not conclude that is because of the fact that there may be a variable that is confounding. There may be a variable that influence the relationship between the two variables of interest that you don't really talk about. You get what I mean? Okay, so there is to, considering an instrumental variable now, we be able to control that. Okay, and that will allow, for the possibility of making causal inferences with the observational data, because it was argued that, okay, the only way we can actually make, causal inferences is when we're working with the experimental data. Of course, working with the experimental data, we basically need to partition participants, okay, into groups using what I call the principle of randomization. And of course, there's a lot of things involved, if you want to consider the ethics wise. And, most of the time, we normally work with the observational studies. And how do we actually translate the association observed in observational study to causation? That is exactly what we mean here. We believe with the use of instrumental variable, of course, we can achieve that. Okay, so the other example, like what we want to talk about, propensity scores. Of course, the instrumental variable can help adjust for both the observed and the unobserved confounding effect. Okay, is there any question before I go to the next slide? Okay, The silence actually implies that you guys are good. Okay, so the next I want to talk about now is conditions that instrumental variable must satisfy. Before we can authoritatively, you get what I mean? Before we can authoritatively say that the instrumental variable introduced has done a great job, we got conditions it must satisfy. Okay, a valid instrumental variable must actually meet condition of relevance and exogeneity conditions. When I say condition of relevance, what we're trying to say, the choosing the choosing um, instrumental variable has to correlate with the predictor variable of interest. The predictor variable is your X. We also call that explanatory variable. We call it feature in machine learning. So there must be a kind of statistical linkage between the instrumental variable you are incorporating and the predictor variable in your model. You get what I mean? And the moment there's a connection between them, then of course it's actually translates to its relevance. It means it's relevant. Okay, that is not the only condition. Another condition is the exogeneity condition. And the exogeneity condition is basically going to say, okay, the instrument you have chosen should not relate with the error time. Of course, don't forget the reason why we find ourselves in this situation is that in the conventional linear regression, a particular X variable of interest was actually correlating with the error time. That was what we're trying to fix. Okay, that was why we introduced the instrumental variable. And you know what? We don't want a situation where the instrumental variable introduced exhibit that similar gesture. We don't want that. Okay. And of course, situation where the instrument is uncorrelated with the error time now, then it means the exogeneity condition has been met. And let me now tell you this, we got a way to investigate the relevance. We actually have statistical procedure to investigate the exogeneity condition of instrumental variable. Okay, so let's go into notations now. Okay, of course, we've been talking about you know, instrumental variable. I think we basically need to, I need to take you back to the conventional linear regression model. Of course, as statistician, the moment we want to characterize relationship between of variables, here now, we're actually talking about the simple linear regression model. You get what I mean? Okay, talking about this particular guy here. Okay, statistician always start by specifying model, right? We specify the functional form of a model. Okay, and of course y equal to beta naught plus beta 1 xi plus ui, and of course the beta naught plus beta 1 xi is basically, when you take a look at this side, that is the deterministic part of the model. Okay, so and why this guy is actually the random part. Of course, the way we specified our statistical model, it is specified in a way that is a combination of deterministic parts and the random parts. And the random part, of course, we know is actually the error term, right? The unobserved. And of course, our assumptions actually centered on that error term. Of course, you know that, right? So, but you know that in the conventional, for me to use OLS to estimate parameters in this regression model now, right? I want to estimate beta naught, I want to estimate beta 1. Okay, I actually need to use an approach that will actually lead to drastic reduction in the unexplained variation. Of course, the unexplained variation, of course, that is actually captured by the error time, which I call the random paths. And of course, we get assumption before that can happen. And if you take a look at the assumption number 1 here, okay, the assumption number 1 is that the expected value of ui given xi must be equal to 0. But let me tell you this, the only condition under which that conditional expectation is going to be equal to 0 is when there is no relationship between the predator x and the error. But in the situation where relationship exists, of course, that's assumption number 1 will be violated. Okay, and when the assumption number 1 is actually violated, then it means we cannot trust our beta 1, even though it may be unbiased, but it's no longer going to be consistent. You get what I mean? And don't forget, when we talk about consistency now, is just the inconsistency in beta 1, the instability in the beta 1 could be attributed to the violation of assumption, because when this assumption is violated, it will actually tell on the variance of beta 1. You get what I mean? Okay, so the second assumption is of the fact that the xi, the coordinate xi, yi have to be independent. And of course, uh, there's nothing, we don't expect to have outliers. Okay, so I think we're basically going to focus on the first assumption, because at time researcher could do a very great job the moment you collect your data randomly, where you allow the principle of randomization. Of course, the independent assumption is expected to hold, and of course, we at times will be very, very careful to be, to make sure we don't have outliers. But you know what? We are not interested in pursuing the violation of number 2 and 3, but the violation of number 1. And let me tell you the threat to internal validity now, when you have a violation of the first one, is what I call the omitted variables. The omitted variables is just like, oh, okay, I'm looking at the relationship between y and s, but there's a particular variable that is missing in this statistical architecture. And maybe we were running away from the problem of multicollinearity. That was why we did not include that in the model in a way. And when you don't include that in the model and you hide that under the error component, of course, your predator variable is still going to be correlating with that. And that will lead us to the problem that we are facing right now. Now, another one is when we have your functional form is specified. In statistical analysis, we start by specifying the functional form of a model. Of course, we need to be guided with statistical theory to be able to specify the correct functional form. So what about measurement error, the sample selection, and simultaneous causality? Okay, I think I'm going to dwell more on the simultaneous causality. One of the reason why we cannot conclude causation and association is because of the fact of what we call the directional problem. So what do we mean by directional problem? If I'm looking at the relationship, if there's an established relationship between y and s, okay, the issue now, which one causes one? Do we say y cause x or x causes y? You may be looking at the relationship between vitamin D intake and depression. You get what I mean? And if you're able to establish relationship between these two variables, of course, the question we're going to ask ourselves, does depression actually causes, reduce intake in vitamin D, or vitamin D intake actually causes depression. So that is what we mean, by simultaneous causality. Okay, when you talk about the system of equations, where you have, situation where this particular predator depend on that, and the other one also depend on a different predator. So that is very common in econometric world. Okay, so far so good, right? Okay, so I'm gonna go to the next slide. Now, like I said, the only condition under which we can use our OLS when we're trying to fit this kind of particular model is when we have this situation. If you take a look at this situation now, why? The outcome variable depend on X, okay, and it depend on the random part. We don't have a situation where there's going to be a connection between X and U. Okay, this is a situation where we actually going to use the OLS, but in a situation where this is the case now, I wanted to take a look at this. You're basically going to see why depend on X, why depend on the error, but at the same time, X and U are correlating. Okay, take a look at it. We cannot use OLS to obtain, the estimates, okay, of the causal effect, because that estimate is no longer going to be reliable, in the sense that there's basically going to be an instability. Okay, so this is another form of that. Give me 1 second. So another form of that is this, you know, this is like a double causality. If you take a look at the simultaneous causality, Y depend on X, X also depend on Y. This is not good at all. It should be a one-way traffic, not a double-way traffic. When you take a look at this, even though there's no relationship between the predator X and the unobserved, but the further relationship exists between, a simultaneous causality exists between X and Y. That's a problem. You get what I mean? Okay, so on that, I'm actually gonna go to the next slide now. Give me 1 second. Okay, so I think you understand that. Okay, so in a in a situation where there's a violation, like I said, I'm actually focusing on this guy, right? And there's a violation of this assumption, right? It's no longer zero, right? Then it means I actually need an instrumental variable. Now, let me tell you how the instrumental variable work. The instrumental variable will actually split, the period variable of interest, X, into two parts. Okay, there's going to be a part, that is correlated with the error time. And there's basically going to be a time that is uncorrelated. That's what you see here. Okay. So that is the job this guy want to do. He's going to do the job of partitioning, because we actually want to believe it's not going to be the entire, initially, it was the entire space of X that was correlating with the error time. But with the introduction of the ZI, which we call the instrumental variable, is basically going to partition that into two. And that will enable us, because we, in our model, for our model to do a very great job, we basically need to isolate, the variation in the predator that is uncorrelated with the error time. That's what we need. Okay. So that is it. That is the job the instrumental variable Z is going to do. I'm going to repeat that again. The instrumental variable Z will actually do the job of splitting the the predator into two parts, the predator xi that we call the explanatory variable xi. Okay, there's going to be in one part, we're going to have situation where it is correlated, where the predator is correlated with the unobserved, and in the second part where it is not correlated. And what we actually need is where it is not correlated with the UI, which is a random component of the model. Okay, in the model. Okay, so which means if I really want to get a consistent estimate of beta 1, what I just need to do is to use the a part, the part of the variation in S that was not, that was not correlating with the error time. That will be actually do a very great job of estimating the consistent estimate, of giving us the consistent estimate of the causa effect of X high on Y high. I wanted to take note of that. Okay, so, but I just wanted to know here, I'm only using the idea of I have one endogenous regressor and one instrument, okay? One endogenous regressor, then one instrument. Okay, so the other time, I actually said that for instrumental variable you introduce to be relevant, you basically, that you need to text assumption underlying the validity of the instrumental variable you are introducing. Okay, you need, because of that, you're basically going to check for relevance of the instrumental variable, and you're also going to check for the exogeneity. And of texting, it means you basically want to see whether the instrumental variable that you have chosen is actually correlate with the endogenous regressor. Okay, you basically want to see the covariance of the instrumental variable z, and the predictor variable of interest must not be equal to 0. And of course, in the test of exogeneity, okay, you basically, we expect that the instrumental variable introduced should not correlate with the error time. And mathematically speaking, how do we actually state that? We're basically going to be this guy here, the covariance of z, okay, and ui has to be equal to 0, which means that's no direct effect on yi. Okay, so that is what I actually explain here. Okay, now what I'm going to show you now is how do we now actually, when we introduce instrumental variable now, how do we go on estimating beta 1? Of course, I said something the other time. We're basically going to do this in 2 stages. Now we're basically going to start with the conventional linear regression. Of course, the reason why we cannot fit this guy to our set of data, because the xi and the ui are correlating. And of course, we actually need instrumental variable z. The instrumental variable z that we're actually going to introduce will help us to isolate, the variation in S that is not correlating with UI. That's exactly what we need. You get what I mean, right? Now we're going to form a new model, right? In the new model, we actually, because if you want to conduct what I call an inference test, we needed another regression model that will be relating the predictor variable, the explanatory variable with the instrumental variable. So which means I'm actually going to have a new set of parameters, the pi 0 and the pi 1. So take a look at that. So if I basically want to test influence now of this particular instrumental variable, the influence on the predator, right, on the X, then I can actually, talk about pi 1, okay, which is basically going to be the new, which is going to be the average contribution of the ZI to the explanatory variable that we talk about. Okay, so we're actually gonna start fitting this guy. We're gonna start with this guy. Okay, we're gonna first start with that guy, and starting with that guy. So that is gonna be the first stage that I'm talking about. Look at that. That is the first stage, right? The first stage, I'm actually going to regress X on Z. Don't forget, my Z is the instrumental variable that I actually introduced. And my X is actually the predictor variable, the explanatory variable, the one you also call independent that was part of the conventional model, linear regression model you stated. You get what I mean? Now, we actually, after that, we needed what I call a predicted values of the XI. That's what we need. Okay. We needed a predicted values of XI. So we need this guy here. Look at that. That's a predicted value because you know why we believe the predicted values. Okay, because there are two different we got two different values now. We got original X and we got predicted X. So we believe the original X was the one that was correlating with the error time. Okay, and don't forget, I said something the other time. We needed to isolate, part of X that was not correlating with the error time. You get what I mean? And fitting this model now, we basically need a predicted values of X, and it is that predicted. If you after getting the predicted values of X, the first from this model now, we don't expect the instrumental variable Z to be correlating with error time. Okay, and that was what we actually, that's what we're trying to say here, that the covariance, okay, between the Z and the U have to be equal to 0. So that we need that for to establish our exogeneity. You get what I mean? So, and let me tell you this, the X cap, the predicted, we contain variation in X, like I said the other time, that is uncorrelated with mu. That is what we're trying to isolate. And that is, by the time we now go back to the model we want to fit here, we're no longer going to be using the original X, but we're actually going to be using the predicted X. And that is what we're going to base our second stage OLS on, where we're basically going to regress Y on the S cap. Take a look at that. Where is the S cap coming from? The predicted actually coming from the fourth stage estimation. Take a look at that, and we are good now. We can use the conventional formula for beta, to do that. Take a look at that. So that's exactly what I mean. Okay, so then at the end of the day, when we get that, so we can now use that on our data. Take a look at that. Going back to the example, where we actually want to apply the knowledge of that to data collected by Professor David Card. Okay, he used the data in his article, using geographic variation in college proximity to estimate a return to schooling. Okay, this guy actually was looking at the effects of education. It's looking at that effect on wage, and we now realize that proximity to college, like for instance, we got some students that live very close to their campus. We have students that live far away from campus. Okay, so it's using that as the idea of the instrumental variable. You get what I mean? Okay, so when you take a look at what I have here, this is like ignoring the fact that the education here will be correlating with the error time. When you go ahead and pursue that, you cannot trust these results. Okay, some of you, when you actually conduct an OLS and you have a significant p-value, don't celebrate yet. Okay, This is an example now. Don't celebrate yet. You know what this guy is giving you now. The result here is trying to tell you that, okay, that is significant and everything looks so good, but that everything does not look so good because the estimate here, okay, the OLS estimate of return to education likely inconsistent due to omitted variables and measurement error because of the fact that, and how do I know that? Of course, we have a test of absorption that can be conducted to see if the independent variable education actually correlating on the unobserved. So Professor Cardier used data from NLS Young Men cohort collected in 1976. Okay, among others, wages and years of education for 3,010 men. Okay, so what I'm trying to the takeaway from here is that you can't trust what I'm showing you now because of the fact that endogeneity problem exists. You got to fix that. Okay, so in an attempt to fix that, so we actually need to isolate variations in the years of education that is uncorrelated with the error time. That was, just like what I said the other time. And this is where we need a very valid instrumental variable. And of course, there could be different candidates of, instrumental variable. Okay, but CAD in 1995 actually uses variation in college proximity as an instrumental variable. That is reasonable. Okay, the proximity to college. If you're looking at the effects of education among student education and the wage, of course, um, what may influence that relationship may be your distance to your college, to your university. You get what I mean? Okay. So, and we also have the following instrumental variable. So the instrumental variable here is used here is more or less categorical in the sense that we call that near college, right? One, if individual grow up in the area within a 4-year college, we have some uh, you know um, some students who actually living around the campus. And we have some students that actually come out of the state. You get what I mean? Okay. I remember when I was in the university in Africa, particularly University of Ibadan, Nigeria. We got some students that are students of of the faculty that actually live on campus. You get what I mean? We even get some students that live on campus. They have their accommodation on campus. Those ones, their lecture rooms, very close to where they live. They don't necessarily need to spend money on transport. You get what I mean? Okay, so zero is individual grow up in area without a 4-year college, because if you're an individual grow up in the area without a 4-year college, that's also can be an issue. So we are actually considering this an instrumental variable. So meaning you grow up in an area with a college, or you grow up in an area without a 4-year college. So that could have effect. Let me tell you how that may have effect here. When you grow up in an area with 4-year college, that may motivate you to actually considering a pursuing education in the first place. Okay. And of course, those who live in an area or who grow up in an area without a 4-year college, that doesn't mean they don't go to college. They go too. But of course, the impact may not be the same. And in the first stage regression we're going to do, we actually need to, when we are introducing an instrumental variable, we need to regress that instrumental variable on the predictor, on the explanatory variable, in order for us to isolate, okay, what are the variation that's, that is not correlating with the error time, which is exactly what we're doing here, okay? And we got a way to investigate whether this really work or not. I think we normally look at the F value. We did get a threshold of 10, and this is already 60.37. You can see that, right? So which means there's a connection between the instrumental variable introduced and the predictor that was the years of education. That was the education, the years of education. Okay, so which means that make that instrumental variable to be valid, and if we are introducing an instrumental variable, we need to regress that instrumental variable on the predictor, on the explanatory variable, in order for us to isolate, okay, what are the variation that's, that is not correlating with the error time, which is exactly what we're doing here, okay? And we got a way to investigate whether this really work or not. I think we normally look at the F value. We did get a threshold of 10, and this is already 60.37. You can see that, right? So which means there's a connection between the instrumental variable introduced and the predictor that was the years of education. That was the education, the years of education. Okay, so which means that make that instrumental variable to be valid. And of course, in the second stage, what we basically going to do is the predicted values of the predicted values of the education now is the one that will be used in the regression proper in the second stage, because we believe that the predicted value of the education now is the one that is uncorrelated with the error time. You get what I mean? So now, then we now rerun that, and this is what we have now. So this can actually be trusted now. But let me tell you, instead of us to perform it, so we may not get an accurate result when we do it stepwise the way we've done it now. So we also have a way to actually perform these two stages in one, uh, you know, once without separating that. Okay, but before I go into that, I'm just trying to show you, the formula that we actually using. Okay, so we regress, in the first stage, we obtain the predicted values of the X, and we're now going to regress Y on that. Of course, our beta curve for the second stage SL, SLS now is going to be this guy here. And you're basically going to see that there's no, comparing this to the conventional OLS, the difference is just like the S cap replace the X. Okay, so this is trying to, like, if you take a look at this part now, and the S cap is that particular model, this is the mean of that, then you trying to simplify that mathematically, we get this, then you plug that in, we have this, and at the end of the day, we basically going to derive, you follow the mathematics around here, you basically going to derive our instrumental variable estimator. As you can see here, finally, the instrumental variable estimator we're only going to have the deviation around y, the deviation around x, and the deviation around the instrumental variable. Okay, because we're basically looking for a way to compute that data once, not going through the first or the second stage that may not actually be accurate. Okay, so this is what I'm talking about. I said we can obtain the two SLS, estimator in two steps as we have seen. But however, the standard errors reported in the second stage regression are incorrect. I mean, the one reported here are not that incorrect. And that is a reason why we needed to derive this formula. And in the end, we can actually, you know, conduct that in just a single step. So that was why I said, like here, I'm actually using Stata, right? I'm using Stata. You can use how, you can use Python. Okay. Now, instead, we can obtain the two SLS, in one step. Okay. But you need a package. Okay. And of course, this is the result. We can actually trust the standard error associated with, our predator now. Okay, so this is where I'm actually gonna stop. Okay, for today. Is there anyone want to ask question? Okay, so I want to appreciate you know everyone for attending my lecture today. Until next time, I call your way with another exciting statistical topic. Make sure you stay safe and have a very good day. Bye for now, everyone.